Okay, so to continue where we were last time around, so we had looked into some of network synchronization protocols, and I had started down this path of how if you have access to some sort of a reference clock over a network, then it can be used to uh, do kind of equivalent of what temperature compensated crystals do. So temperature compensated crystals have a local sensor. They are calibrated in the factory. There's usually some sort of a memory or some sort of circuit where they kind of put the calibration parameters, so they subject it to different temperatures, and for that particular crystal, they basically come up with the correction curve. And that costs, which is why TCXOs are costly, and depending upon the kind of accuracy you need, there could be many dollars, many tens of dollars even. So, alternatively, if you do have access to some sort of a network source or GPS or whatnot, then that could become your calibration mechanism, and together with if you have some sort of a local temperature sensor. So, in the network context, some of the people have explored that concept, and talked about the idea basically is that when you start out, you have no idea of what um, no idea of what the calibration setting is, and what ends up happening is that you are going to synchronize much more frequently. So since you don't know the mapping, so you're going to refer to the reference clock much more frequently. But each time you're doing it, as you learn your clock's drift characteristics, the idea is you kind of note it down by also looking at the temperature sensor that you have. And then over time, as your mapping becomes fleshed out, then you have to refer to the reference less and less. Now, there are still going to be remaining factors like the clock ages, your temperature sensor itself is not perfect. So all these, to take all these things into account, you still will have to keep syncing back to the reference, but the frequency can be lowered enough so that the cost of time synchronization, because otherwise you're kind of frequently sending these messages back and forth, the cost of that kind of goes down. So your system starts out with a relatively high communication cost and then gradually kind of settles into some quiescent state. Furthermore, crystals that may be more sitting in more stable environment, you would see that they would refer to the reference much less so than, let's say, something which is sitting outdoors, seeing much more extremes of temperature, or like when there is a shade to sunlight kind of transition. So this concept in various forms, several papers in past 4 or 5 years have kind of explored. And kind of for very low end devices, so like a lot of wireless sensors and all, where everything is the cost is severely constrained, these kind of approaches kind of become attractive because you do have some sort of a base station, and that base station does have some sort of a long-term stable clock. So that I talked about last time. So what ends up also happening in these cases, as the temperature varies more, you would see that these systems kind of refer to the reference more often. So this is an example which is showing that over time, due to the day-night pattern, you would see that how often the node refers back to the gateway. So kind of the beaconing interval changes. So that was one point. The other one which I wanted to go over was another area that people have explored is this tension between. There was a slide I had. Let's see. This one. This tension between that granularity and power and stability. So good quality clocks do, besides dollar cost, do cost you in terms of power also. So as this thing shows, that as you pay for frequency, so the resolution with which you are able to measure time, as we go from 32 kilohertz to megahertz kind of things, we are paying for more power. And the other thing is that as you if you go for a more stable clock, so like look at the bottom two rows, you also going from 25 ppm to 1 ppm costs a lot of power. So now your system doesn't always need the same stability, doesn't always necessarily need the same frequency even. So, but at the same time, your oscillators are kind of you commit to it, and you have kind of that's what you end up using. So, concept that sort of people have explored is much like in processing and other contexts where we kind of take a let's say a microcontroller and a big processor and then switch back and forth between them. You can imagine doing the same kind of thing with oscillators also at various levels. So it could be multiple oscillators you're switching between, or it could be a single oscillator but it has different resonators and you can lower down switch between those resonators, all with the goal that as the needs for the system change in terms of stability, in terms of frequency, you could do it. So frequency changing, we saw, could also be done by the PLLs. But with the PLL, your basic clock source oscillator is still the same. That's not changing. It's only the PLL parameters are changing. So you do gain some stuff because PLL itself, its efficiency is going to change, and PLLs can account for as much as half the power consumption of overall clocking system. But let's imagine now you're designing something where you go into deep sleep and all. And now leaving that, again, going back to the same table, leaving even that 8 megahertz crystal on at a milliwatt power consumption could be make a huge difference between lifetime versus, let's say, something which is at the microwatts. So when you go into sleep, you would perhaps like to switch over to much lower power clock source. So this this concept of duty cycling or switching back and forth is something, again, several groups have explored in recent years. Now there are issues which come up in this picture. One is you have to transition from a clock very carefully, otherwise your edges might be dirty. Another issue which comes up is waking up. So let's imagine when you go to sleep and you decide that, okay, I'm going to switch to the RTC that your systems have. It give you a 1 second pulse typically. What that also means is that the granularity at which you can wake up is now going to be a 1 second, and that may not be sufficient for things like when you have to send a packet at a very precise time. Okay, because packets are at the order of milliseconds. If you're using this mechanism for some communication type system, then your wake up has to be kind of finely synchronized also. Likewise, you may also face issues like an event comes and you wake up and you have to timestamp the event, but if at the time of wake up you're relying on this coarse clock, then your event timestamp is very coarse, and that may cause problems. So, but otherwise, kind of the basic idea is that there's a fast clock, there is a slow clock, and when some sort of an event happens, you want the timestamping accuracy and whatnot of a fast clock, but while you're dormant, you would like the power efficiency of a slow clock. And now, at some level, this is a non-solvable problem because if you have truly turned off your high-frequency clock, and when you wake up, all you have is your low-frequency clock, then that's what you have to live with. But in many systems, duty cycling is done on a fairly regular basis. You do have some sense of when the event is going to happen, perhaps some time window. So the idea is you go to sleep, and then at the expected time window, you switch to the fast clock. That clock will take some time to stabilize and all, and then you kind of work off that clock. So in applications where the system is largely asleep, and then occasionally there are these events, and perhaps you're polling for those events in a duty cycle fashion, or perhaps you know that when the event is going to happen, roughly speaking, in a communication setting, then you can do this kind of switching back and forth. And now, this idea has been explored more at the level of people designing systems, but you can imagine kind of the same thing being applied within an oscillator also. So the system can tell the oscillator, wake me up at this time, and then this is the precision, and then the oscillator can kind of then decide what kind of resonator it should activate to achieve that goal. So you could imagine this kind of smartness pull down. So currently the oscillators that you buy have some degree of configurability into it. So for example, because when we buy a oscillator, its frequency is not exactly the same. So many oscillators which are used for precision application, they allow you to talk back and correct the frequency a little bit. So you can apply correcting factor. You can tweak it a little bit, but it's really meant for kind of a fine tuning. So it's like you're buying something, it has gotten its frequency specified, to be, let's say, 10 megahertz, maybe you can tweak it between 10 plus minus delta so that you can calibrate it precisely. So what happens is, for example, if you are a receiver in a communication setting, you have a 10 megahertz crystal, there's transmitter which has a 10 megahertz crystal, but they are slightly apart. So when the packet comes in, you have the preamble, and from the preamble you learn that there is an offset of delta in your frequency versus the transmitter versus that transmitter's. So then what you'll do is you'll tell your clock to shift the frequency by that tiny amount delta, so that then you can sample the incoming packet very accurately. And then when the next packet comes, you're going to play the same game again, because it might be a different sender, maybe the drifts may have changed. So this tiny amount of tuning always happens. But this drastic tuning, where you have your system is going through very different modes of operation, currently is kind of done by having multiple oscillators switching back and forth. So with embeds, for example, like the example I'd given last time around, there was a crystal oscillator, there was the RTC clock, there was the on-chip ring oscillator, sorry, on-chip RC oscillator. All of them had different characteristics, and you could switch back and forth between them. So maybe there are times, like for example, imagine that most of the time the system is asleep, but every morning it has to wake up and very accurately timestamp something. So maybe rest of the time while you're mostly asleep, you can operate off the RC clock, because all you need to do is to run. But then and then the RTC kind of wakes you up, and then you switch to the high frequency clock. Perhaps activate your GPS, get a precise time sync, precise time information, and then operate on your high frequency clock, high resolution clock for a while to timestamp the event very accurately. So you could play these kind of games to the extent system allows you to. Okay, so playing these kind of things. So this was some work on a paper. What it shows is that if you apply this kind of dual clock kind of stuff, where you have combining these kind of ideas, so dual clock, temperature compensation, and all. So FTSP, which I previously talked about, which was giving like a couple of microsecond per hop kind of delay with something like this. The spread, you can bring the spread down to like 0.5 microsecond kind of spread. So existing protocols can be improved by kind of just improving the clock. Going further down, if you recall, I had last time this picture showing the inherent uncertainty in the radios that these things currently use, and that itself was plus minus 0.2 microseconds kind of thing. So you're basically hitting the radio limits, and going further basically means that you just need something which is a communication system with a more deterministic characteristic. So we saw how you can synchronize two nodes. We saw things you could do at the software and system level to kind of get more mileage out of the technologies. The next issue comes up is that what happens over multiple hops. So a lot of networks have nodes where you are more than one hop away from a time reference. And so this is, in these kind of things, essentially you want the whole network to synchronize, because they're collectively doing some sensing tasks, some sort of an actuation task. So that leads to this notion of peer-to-peer time synchronization, which is you want to take two arbitrary nodes in the network and relate their time to each other. So one way of looking at it is a time coordinate conversion problem. So each node has its own time coordinate system, and we want to come up with a transform which can take time expressed in one node's coordinate system and map it into another node's coordinate system. Now, one way to achieve it is to have the global time sync, but there are other, in some application, there are other ways one could go around it. So, for example, one notion which people have explored is something called post-facto synchronization, or after-the-fact synchronization. So previously, when we looked at synchronization, we were always looking forward in time. So our clocks were synchronizing, and we were learning their drift, and then we were projecting in forward, saying how much would my clock drift away from someone else's. But physics of clocks is obviously reversible in time, so you could go back in time also. So let's imagine a node sends you something, an event saying this event happened at time t according to that node's clock, and it wakes you up. Now what you could do is you can synchronize now after the event has happened, but keep track of how much delay happened in that process when the event reported it. And then you learn your drift, and then use that drift to go back in past, because our assumption that drift is stable, that is clock offset is changing linearly over short time intervals, is equally valid going in the past also. So what this model would do is that instead of paying the cost for synchronization all the time, you basically, when the event happens, you keep track of the delay from when the event happens, so that the sending node can do. And then you synchronize, learn the drift, and you correct back in the past. So you can sort of something which happened in the immediate past, you can get an accurate timestamp for it still. Now, this is, of course, not always possible. It doesn't make sense if I have to schedule to do something in the future. If I have to schedule that the two nodes should act together at 1 p.m., then, of course, I have to go forward in time. But in many sensing applications, this post facto concept works out. So the standard question is what time it is, but oftentimes you really care about what is the time difference, or what was the time difference a little bit in the past. Clocks start out unsynchronized, they remain unsynchronized. A set of receivers are waiting for some interesting event, someone saw something, it locally timestamps, and then they reconcile the clock, learn the drift, go back in the past, and get an accurate timestamp of something which happened relatively recently. All that means is that this adds up to the latency with which you would be able to report an inference about the event. If, for example, on the other hand, clocks were always synchronized, then as soon as the event happened, you would know its precise time, and you would immediately be able to say something about it. For example, maybe you were using this thing to learn the speed of the target or the nature of the target, so you would be able to act upon it immediately. Whereas in this case, there will be some short delay, some message exchanges, but oftentimes that's perfectly fine, because physical world, a lot of things are at tens of milliseconds kind of delays, whereas you're talking about doing the communication at microseconds. So the speed of communication is to your advantage. So what this is doing is it's basically avoiding that background energy wastage, which you would otherwise need to have, where all the nodes are synced kind of all the time. So that's an example of how not blindly following let's sync all the time, let's have high quality all the time can kind of make a huge difference. So this is kind of a stylized version of it, where basically nodes are observing for events, and then using, let's say, RBS, which we saw last time, receiver radio broadcast synchronization. When they see something, they advertise, hey, I saw something at this stage, I saw something at this time. Each node is doing it independently, and then after the fact, you reconcile them. So they do some message exchange to learn their clock drifts, and make the assumption that the clock drift was the same in recent past, and go back in time and correct some things. So that's one concept. The other thing which again some years ago people did, which is, now imagine I have a network, and through the mechanisms that we discussed last time, sender, receiver, and the two variants of sender, receiver. What's happening is nodes are learning the relationship of their clocks to some neighbor's clocks. So for example, through RBS, so let's say A does a radio broadcast, then all the nodes in its vicinity learn their mutual offsets. And likewise, when C transmits, everything in its radio range learn their clock offsets, and so on and so forth. So what you end up with is kind of a graph of all the nodes in the network, where edges represent which nodes know the clock offsets or clock drifts between them. So not everyone knows between everything. So two nodes may be too far away to know what the offset is, but nearby nodes would know this thing. So you essentially have this kind of a constraint graph. And now let's imagine that this top left node and this bottom right node, they want to convert time from one to each other. So I may have different pathways. I can say, okay, this node, top left, the offset between this and this node out here is something. And then I can say, I can add to it the offset from this node here and here. So I can kind of take this path and add up all the offsets according to this. But likewise, I have many different paths, and since each measurement is noisy, depending upon which path I take to the network, I may actually get different characteristics. Um, you could think of this thing as kind of a time routing problem. That is, I want to find, if I need to convert my time to some other node's time, your goal is to find the shortest time time in the sense of best quality of time that would yield through the constraints that you have. And sometimes you may need to combine multiple results. So like, for example, again, let's say this top left node and this bottom, this node out here, they want to find their offset. They have a direct measurement, but then they also have a couple of indirect measurements. There is measurement like this, and there's a measurement like this. Maybe, just maybe, it's possible that the communication channel along these edges of the square are much better than along the diagonal, because of reasons of nature of length and whatnot. So if you look at everything, then all the paths, and look at the uncertainty that is in there, you may be able to end up with a better measure. So these kind of problems where you have a graph with edges that have constraints, and then you're trying to find some values of the nodes such that the constraints are all satisfied, is something that occurs in many disciplines. In fact, another example where something like this happens is location. So let's imagine each one of these was a network node, and each edge represents a distance measurement, which could be obtained by, let's say, exchanging radio packet or acoustic packet or something like that. So what I have is now a graph where I have a bunch of pairwise measurements telling me distance between neighboring nodes, and your problem now becomes find relative values of locations for all these nodes which best satisfy the constraints that the measurements are imposing. So time synchronization problem across this is a very similar flavor, which is I have a bunch of pairwise measurements telling me how apart the two clocks are, and your goal is to come up to assign a single number, a single drift number, or a single time value to each one of the nodes such that those constraints are maximally satisfied. And this has been a topic of a lot of interest among the more theoretical types, because you want to come up with algorithms that are efficient, don't eat up a whole lot of bandwidth, give you good quality results. There's some work out of Illinois a few years ago kind of showed that you can model this whole thing as like an electrical network, where the pairwise measurements can be viewed as impedances, and then using standard electrical system theory, you can come up with a solution. When you solve for it, you essentially get the clock parameters out of it. But generally, this is a class of distributed optimization problems which are seen in many other domains as well. So in time synchronization context, it's called the time routing problem. And one of the very first paper on this work was collaboration between some folks here at UCLA and Dick Karp, who's a very famous computer science theorist at Berkeley. They kind of did some of the initial work, and then a lot of other people picked it up. Once you have this basic mechanism, then absolute time synchronization is just, all it means is that one of the nodes perhaps has a reference clock attached to it. So it's a GPS node. Or it may be that multiple nodes have GPS attached to them. So and you can think of these nodes as anchor nodes, that these nodes are anchored to the global time, and you could say they have perfect accuracy, and then the rest of the nodes are going to sync to them. So if I don't have any anchor node, then no one knows their absolute time. But I can still given a rich enough graph, I should be able to come up with an assignment which is relatively consistent, even though I don't know the absolute values, but I can come up with relative offsets. But if I have an anchor node, then I can anchor the whole thing into actual real wall clock time. In location context, what it means is, so if by that analogy, if these things were representing distances, imagine like these were each one of these things was a sensor node, distance measurements, and I didn't have an anchor node. Then you can imagine that if you have enough of these edges, then I would at some stage have a rigid graph, and which means a rigid graph means I have relatively localized it, but it could be oriented whichever way in 3D space. But moment I begin to know actual location knowledge for some of the nodes, then that rigid body would be anchored in space at a particular location. So in case of time, the analogy is that if I have GPS or some other source of actual time knowledge at some of the nodes, then I would begin to know the absolute time. In the absence of that, all you would learn are the relative time differences. Okay. So yeah, in these kind of models, what's happening is we are not running any sort of a global NTP kind of stuff out here. In NTP, what would happen is we would designate one node to be a server, and then in a simplest implementation of NTP, and then everyone else will talk to that server. So what's happening is we are actually not considering the structure of the graph in that. I mean, we have overlaid kind of a one-hop tree on top of a richer topology. But in reality, if you take into account the underlying topology, you could do a lot better. Of course, at the cost that every node is now participating in your time synchronization protocol. NTP's advantage is that intermediate nodes in the network, you have no interaction with them. You're just jumping straight to the server that you're talking to. But it comes at the cost that you are not able to take into account the individual hop characteristics that you may have. So this kind of approach became very, came out of kind of ad hoc network, sensor network kind of communities and all. As I mentioned, there are, what should I show out here? Yeah, this kind of shows that, of course, as number of hop increases, you are going to see worse and worse. So nodes which are farther apart are going to have poorer quality, time quality between them. Some work out of Santa Barbara in recent years has shown that how network topology matters. So you might imagine that if I give you 10 nodes, and if those 10 nodes are in a straight line, versus the same 10 nodes are configured, for example, a node in the middle and the other 9 around it, so that every node is within 2 hops of each other, they will exhibit very different quality in terms of time synchronization. So what these guys showed is that the logical topology, who can talk to who. So you basically have the same number of nodes and same number of nodes per number of measurements per edge. These two networks have the same property in that regard, but this is kind of more random looking topology, and this is kind of a more lower dimensional topology, if you may. What they showed is that the performance characteristics would be very different in terms of how, as you scale that, as you look at a node and how far away it is from the node which is the anchor node, the reference node, the two graphs which otherwise have identical characteristics other than their topology, they end up having very different characteristics. So network topology matters. In some cases, network topology may be something you can control, because you may, for example, spend more power to communicate longer distance. In other cases, a topology may be what it is given to you, but so maybe you can say something about how well I'm going to do. So topology matters. Go ahead. Mm-hmm. Yeah, I mean, this work has a bit of an unsatisfying characteristic, which is they have this funny measure. They say same number of nodes per number of measurements out there. So they're actually normalizing the number of nodes to the ratio to the number of measurements which are out there. Okay, but ultimately it does relate to the logical topology as opposed to the physical topology. Okay, so in the sense that these nodes in physical space may be embedded the same way. It's just that which communication links you chose to activate affects your logical topology. And they're obviously glossing over things like if I have two nodes which are far away communicating, then they may have a higher chance of collision with some other nodes. So the assumptions out here are you have infinite number of communication channels, one per communication link, so that there is no conflict. So it's a very idealized model, but I think general conclusions will probably still hold true. Topology will matter, and intuitively speaking, you can imagine, depending upon the dimensionality of the network, if the network is one-dimensional, the average distance from the reference node is going to be different, and moreover, the average number of paths that you have to the reference node are different. So the difference between these two is not simply that nodes are perhaps farther away out here from reference node, but it's also that from a node out here to the reference node, you have fewer paths available than in this case. So you have more measurement opportunities, more time routes available in this kind of topology than out here, and therefore if each one of them is a noisy measurement, you are basically going to end up with a more accurate measurement because you have more diversity in one case. So that's really kind of what the magic that's happening out here. So some topologies give you more ways of reaching the anchor, and therefore you have more paths along which you can get an estimate, and they're independent estimates, and therefore you get a better quality result. So people have explored from this theoretical perspective quite a bit as to what one can achieve under different type of topologies, different kind of scenarios. How fast should I sync? What are good ways of solving this distributed problem that one has? Because ultimately, time synchronization is essentially very broadly a class of that problems which are called as distributed consensus problems. So consensus problems have a rich history in computer science, which basically say, could we get everyone to agree? Okay, so there is some variable, and we want everyone to agree that on a common value for it. And clock, in some sense, is saying that we want to have everyone have kind of a common understanding of what the time is. So you can think of it as very generally in that category of problems with its specialized twists which time synchronization brings. In recent years, people have also tried to improve upon those things like FTSP and all I mentioned to kind of push things. What's the best we could do? Are there other additional tricks and all that one can play so that with existing hardware we could do kind of fancier and fancier things? So some work I think from out of Italy called pulse sync. They basically what they try to do is to create some additional improvements over FTSP, which is a number of years old, and they basically try to speed up the dissemination of time information. So they play some games so that instead of packet by packet as you're moving from hop, time information kind of just seeps through in one go. The main advantage is that if you do things faster, then the drift effect lowers down, and so in FTSP, as the distance was increasing, the synchronization error was getting worse like this, whereas with their scheme it grows a lot slower. So there are sort of, I guess the point out here was there are more recent innovations that people have been doing. So one which I wanted to kind of talk about a bit more was Glossy work again out of Europe 3 years ago, as you can see, and what they did was they basically combined time synchronization with flooding. So flooding is a very well-studied problem in networking. It basically says one node has a data item, and we need to make it available to everyone else. Okay, a lot of network protocols deep down depend upon flooding, but flooding is also often useful as a higher level primitive. I may have a command, I want all the sensor nodes to learn it. And of course, one approach is I contact each one of them. That's slow, inefficient. Another one is I send it out to my neighbors, and each one of them sends it out, and each one of them sends it out. Well, that's also a problem because there is too much excessive transmissions happening. So people over the years have spent a lot of time on what's the best I could do, right? If I knew the network topology and all, I could perhaps arrange for the transmission just the right way, and assuming perfect links and all. So, but generally speaking, none of those assumptions hold. So it's a complicated problem to get right in real networks. So what we have is one initiator, multiple receivers. Some of them could be multiple hops away. And what we are doing is we want to propagate packets as fast as possible and do so reliably. So Glossy builds upon this pulse sync idea from previous. So the problem in blind flooding, that is, I send it to my neighbors, those neighbors blindly send to others, and so on and so forth, is that you basically have an explosion in collisions. So a common approach that then becomes is that you identify, based upon knowledge of the topology of the network, you identify some packets to be responsible for relaying. So you may select, say, if not every packet is going to replicate, only some packet are going to rebroadcast so that you reduce the chance of this collision. What Glossy does is it leverages time sync in a sort of a cute way, and so that it gets a single pass flooding. Okay, so the idea is in one go, it just seeks to get packets out as fast as possible. So the way it does is it basically says, I'm going to operate my network into two modes. Periodically, the network will go into a flooding mode, okay, where all it is going to do is flooding, all the other application traffic is disabled. And that sounds bad, but it's not necessarily bad. I mean, you could just think of like I have a server which every so often is coming in and is going to do the flooding and anything which needs to be flooded during that time interval. So from a very high level perspective, my network system is flooding, goes into rest of the application traffic, then again does flooding, and so on and so forth. And what it does is it performs synchronous transmission for doing fast flooding. So the basic idea is the following. Let's imagine I have two nodes, T1 and T2. And they're flooding the same packet. Now, normally when you flood, packets collide and the packets are lost. But what if the two packets were sent exactly at the same time? Okay, and also for the moment assume that the path lengths between transmitter to receiver are exactly the same. Okay, so the nodes are perfectly time synced. They send out the packets exactly at the same time. The clock frequencies are exactly the same. The path delays are exactly the same. So what will happen at R is it will get two copies of the packet, which will overlap perfectly in time. And since the contents are the same also, it would be able to recover the packet, right? So identical packets, because it's flooding, totally overlapped in time, everything precisely aligned. Now you can imagine I can begin to relax some of these things. So obviously T1 and T2 will not be perfectly aligned. The path delays between T2 and R and T1 and R is not going to be exactly the same. And that's fine. But as long as the packets are roughly aligned out here, I would still be able to detect it. So as long as this misalignment delta is a relatively small fraction of the duration of a bit, then I'm still be able to recover it. And this kind of technique in more general wireless recently has also caught on, and it's called multi-user detection. I can be receiving two different packets from two users and still be able to separate them out. This is a very specialized case of that. So if T1 and T2 were time synced, and now if they were to do rebroadcast, then the node R, which is an additional hop away, would still be able to receive them, and we are not losing any of the packets. So R receives packet with a very high probability if, in case of this particular radio running on some particular TI chip, is less than half a microsecond. Okay, so these are radios of roughly 250 kilobit per second type radios, and it's basically saying that if delta is less than 0.5 microseconds, and since we are talking about relatively local area network, so asymmetry is not so much because of the differences in distances, it's really because of your time synchronization. So the way it works is the initiator sends out a packet. Nodes which are one hop away are going to receive those packets, and they are going to rebroadcast. And since they are time synced, the next hop, even so, a node like this out here, even though a node like this out here is receiving the rebroadcasted packet from this node as well as this node, but it would still be able to recover them. So you are not losing any packets, unlike in a traditional time sync where transmissions are not time synchronized. So good time sync can make flooding make flooding extremely efficient. And generally speaking, I mean, this goes to this thing that time sync, or good knowledge of time, by reducing possibilities of collisions and by reducing the time it takes to learn the sender's characteristics, can improve communication efficiencies. So what happens now is that when Glossy the protocol starts, initiator turns on the radio, transmits a packet. So what's happening out here is a packet is going out, and some receivers are going to receive the packet, others are not. And then what this guy, what the one hop receiver does is it sends out, it takes the packet that it receives and it sends it out, and it sends it out synchronously with all the other nodes. So all these yellow colored nodes kind of send them out at the same time. Now, of course, the packets they transmit are going to be received by nodes which are 2 hops away from the initiator, but the initiator also is going to receive them. So initiator will also receive this packet out here. And this, so this overhearing property of initiator tells the initiator that, okay, did the packet go through? And if not, then it can retransmit. So the so the whole network is going to be operating in this lockstep mode. And this process continues. The second hop receivers retransmit. They will be heard by the 3 hop receivers, but then their transmission will also be heard by original 1 hop neighbor transmitters, and kind of the whole process continues. What's happening throughout this thing is that everyone is also estimating all the time slots, and also these communications are also resulting in things getting synchronized. So there are this slot interval out here is constant for everyone, and each node kind of maintains an estimate of the T slot as it overhears these things. It kind of keeps correcting stuff, and there is a reference time information which is carried within these packets. So as part of the same mechanism, synchronization is also happening. Go ahead.
It's kind of fragile, right? I mean, if one node is slightly out of sync for any reason, then it breaks the entire thing, right?
If that is true, but that's probably true even for regular synchronization protocols. Like take the time routing and stuff like that. You can imagine attacks there where one node is compromised and it basically would begin to think. Now, fragility will depend upon topology in part, right? I mean, if this node, now I guess the point out here is this node, a node here can cause more havoc because the overlap can affect a whole bunch of other things. But the effect will still be within its neighborhood, because if it's misaligned, it will affect the immediate vicinity, but not nodes which are far away. But unfortunately, there's not going to be an easy way to get out of these things in other settings. But malicious nodes, or just a node being buggy for whatever reason, there are calibration parameters that they're relying on very carefully in this case also. So they implemented it on very low-end device. So TI makes a whole bunch of these chips, which are radios and processors kind of integrated in the same chips, originally from a company called Chipcon, which they had bought. So some of the challenges out here, you need to start execution exactly at the same time. You have to compensate for hardware variation. So we saw that those radios do have some minor variations in their thing, and they were already roughly in the half a microsecond territory, if you recall, the variations on the radio. So you have to kind of compensate for that as well. You have to make sure that the execution time is deterministic. So your different pathways through your code should take the same time, because so you say, hey, I want to transmit, and at different nodes, by the time they actually send the packet out for transmission, there will be some variations in there. So they basically resorted to a lot of things. So for example, the radio offers a particular pin. That particular TI radio has a pin which asserts a signal corresponding to symbol being detected by the radio hardware at the lowest level. What they also do is they execute a variable number of no-ops at runtime to determine the variation. So like if the crystal oscillators are slightly different and whatnot, they kind of learn that how many no-ops will take me to actually achieve a particular delay, and they calibrate it across the radios. They also try to do things like constant number of instructions, things like that, through different code pathways. So it's a very carefully designed piece of software, because you have to make sure everything is deterministic, even though you have all these other variations which are likely present. They pulled it off in the sense that they were able to achieve their goal of the delta being less than half a microsecond. And what they achieved with this was 0.4 microsecond at hop number 8. So it's a per hop of 0.05 microsecond, which is pretty amazing. in terms of where we started out. Okay, so by all these careful calibrations and all, they basically are able to achieve a very, very tight time sync um, with pretty ordinary crystals. The crystals on these devices are 50 ppm, 40 ppm kind of thing. So so this is sort of pretty impressive performance. Of course, there are issues usability-wise. So besides what Mark mentioned, it is fragile in a way. So a node, improperly working node, can cause issues, can cause serious issues. The other thing is this usage model, that the whole network goes to sync together and does this flooding. So this partly also means that your flooding stuff has to wait until the next opportunity. So the flooding can see more latency, and you really don't have any control over it. Likewise, while you are flooding, some other higher priority packet may have to wait. So it does have implications on rest of the traffic, but if you can live with this thing, then it's great. Sustain this heartbeat, and along with the heartbeat, you're also flooding stuff. Okay, so flooding information also. So you're kind of double dipping in terms of what you're getting out of this mechanism. So even it's a 3-year-old piece of work, but I don't think I've seen anything significantly better since. So 0.4 microsecond over 8 hops is what you can imagine. Like if you're doing low-end wireless sensor nodes, one can achieve with these kind of things, basically, mechanisms. So kind of things that one has to worry about when doing the time sync and all, and in kind of modeling clock drifts. A lot of these things are relying on learning or calibrating against the clock drift and taking actions to in the design to kind of compensate for it. This particular scheme also suffers from constant broadcast. So this goes back to this issue. I don't necessarily need that 0.4 microsecond all the time. So I'm basically paying this penalty all the time in this particular case. And other issues, we kind of talked about some of the distributed algorithms to make that time routing happen and all. They may not be possible just in the class of nodes that exist. So a lot of work in time sync has happened, keeps happening, because foundationally it is a very critical piece. Knowledge of time, again, kind of at various time granularity, kind of becomes very important. So the approaches I described are not the only ones. There are a whole bunch of other schemes which are which have been there in the literature. This kind of a sampling. One class of schemes basically treats it as a consensus problem. So as I mentioned earlier, consensus problems are those where we want nodes in the network to agree upon something. And in this case, the agreement is that what is the offset vector, right? So we are basically, the value we are seeking to learn is that we can declare one node to be reference, and we are basically saying what are the offsets of all the other nodes, right? And that's a vector that we want everyone to learn, so that then they can, then they are effectively synchronized. So one way of solving consensus problems have often been kind of this kind of strategy. So I will have an estimate for that consensus variable. So let's call it x. I would say I believe x is so much. All of you hear that x. You have your own local estimate of x. You are going to take an average of your estimate and what I advertised. And then you do the same thing. So you will take the average of what you heard, what you have, and you are going to rebroadcast. Others will hear it. They'll play the same game. So all of us are doing the strategy that whatever we hear and whatever we believe, we take an average of the two, and from that point on, we advertise that, and we keep correcting for this thing. So it's a very straightforward strategy, and under many circumstances, you could show that it actually converges. So, and this strategy has been used for a lot of things, like what's the average temperature among a bunch of sensor nodes. In this case, it is about offset. Alternatively, you could use this thing just once you learn the offset, you can synchronize your clock. So what's happening is that nodes are adjusting their clocks to reach synchrony, basically, by kind of this averaging kind of behavior, and as long as the network is connected, that happens. So inspiration. So there are many other ways of solving consensus problem, but this is one. And the inspiration for this actually comes from biology. So I had mentioned earlier that how in nature there exists some synchronization phenomenon, and one which and there are many such things, but one which actually caught a lot of fascination in 1930s or so were these observations by some biologists visiting, I think it was Malaysia or something, Malaysia, Thailand, where in the swamps there are these fireflies, and then apparently kind of at night they all glow in synchrony. Later, they also discovered these things like in Appalachian mountains here. So there are other insects and all which kind of exhibit the same kind of thing. So these are essentially insects which at night they start out desynchronized and then gradually they just all blink in synchrony. And early on, a lot of this became part and parcel of this thing. Is it evidence of some invisible hand of God or intelligence design or those kind of things? But then some analysis later on showed that actually these kind of things can be explained via essentially that the network has a self-convergent property. So you don't really need any controlling entity to do it, but a bunch of independently acting nodes which are interacting in some way can, without any controlling factor, can get this kind of a deterministic pattern or something which is a lot more structured. So synchronous flashing fireflies, same thing, spiking neurons. So I mentioned when I started out this time saying that how brain itself has a clock of its own from the thalamus, which kind of then orchestrates all the other neurons. But the thalamus itself has a bunch of neurons. They independently fire. They're pretty bad oscillators. If you let them oscillate, they will show some oscillation frequency, but they're all over the map. But the collective actually fires with a pretty deterministic rate. So nature is littered with these cases where independent oscillators, when put together, collectively oscillate in synchrony or exhibit other sort of phenomena together. So in late 80s, 90s, some people out of Harvard and NYU and all, they kind of worked out. So interesting thing. This phenomenon was known. This mathematician out of NYU kind of did a very brute force thing. He basically modeled the oscillators as circuits, RC and all, and ran simulations. And he found that, and he had a simple hypothesis, and he kind of tried it out, and it kept working for larger and larger and larger networks and all. And then kind of a person at Harvard working with another mathematician formally proved that for almost all networks that synchrony holds true. So that was kind of the first evidence that actually it's mathematically provable. So the basic idea behind these, the model that is used is the following. Each node is a free-running oscillator, but nodes are coupled. So what happens is at the node there is a variable. That variable is increasing at a particular rate, and that rate is roughly similar at all the nodes. So this rate, but for now imagine that they're identical. So the rate, this variable dx over dt is a constant value. But when x reaches a threshold, then x is reset to 0. So essentially what is happening is that imagine a capacitor to which we are charging with a constant current. So the charge is building up. At some stage, the charge reaches a threshold. Therefore, voltage reaches a threshold. And then a switch closes. The capacitor dumps the charge. And the whole process starts again. Okay, that's a basic oscillator. With a trick out here, additional thing out here, that whenever a node sees some other node being reset, so when another firefly flashes, then the node which saw it, it will change its value of x also. So x has two factors now. Normally, if the oscillator was in isolation, x will keep increasing at this dx over dt. But whenever it sees some other node fire, then it will bump x up or down by some tiny amount. So the idea being that I'm trying to synchronize with you. If I see you, whatever, fire, and I haven't fired, then maybe I'll try to come closer to you. So I'm going to bump up the value of X that I have by a tiny amount. And I keep doing this process, and the idea is that eventually everything kind of becomes synchronized. So nodes fire a pulse after reaching a designated threshold, and then whenever and the coupling is that whenever you see another node fire, then you change your clock value by a tiny amount. So this work, which I was mentioning, Strogatz was at Harvard, and I don't know where Merulo was. They proved that synchronization of a network where oscillators are pulse coupled in this particular fashion would lead into almost all networks synchronizing. That is, if you consider all possibilities, under these assumptions, uniform coupling, zero delay between firing and receiving, everyone can listen to everyone, none of which are true in reality. But that was the first result which showed that under some circumstance, at least they could do. Since then, all those assumptions have been relaxed and all. There's still many open problems, but like nodes can be heterogeneous, the network may not be fully coupled and all, and they have shown that, again, sort of the synchronization property holds true. So this kind of approach has also been very attractive in ad hoc networks because they are also kind of like Firefly networks. Some nodes can talk to some other nodes and all, and this scheme sounds some kind of a natural fit. So instead of locking to a central clock or to a specific node as FTSP or NTP and all do, here essentially what's happening is everyone is identical, everyone is just making local observations, and then gradually everyone's clock will get in synchrony. Okay, that's kind of the basic concept out here. And the mathematics behind it actually tends to be a little bit tricky. In fact, there's a book by Strogatz which I was reading, and in the process of doing it, they actually had to kind of develop some new mathematical techniques, and this kind of relates to chaos theory and also, so which was also emerging around that time. So, but mathematically, each node maintains an internal state x of t. A pulse is emitted whenever x of t equals to 1. The state variable, so whenever x of t reaches 1, it is reset back to 0. So essentially what's happening is that so that's reset function, and then otherwise in the free running mode, x of at each node xi of t is increasing according to some particular function. That's the oscillation function. Without coupling, each node would be periodic with the same frequency but not synchronized because f is the same at every node. So each node will free running, will have some frequency, but they will be misaligned. If a neighbor fires, then the state variable is updated according to this equation, that if I see a neighbor fire, then I'm going to update, ith node is going to update its state variable by some factor out here, where g is some function with some mathematical properties and so on and so forth. So the idea being you kind of just try to come a teeny bit close to your neighbor. And so the overall system of equations can be kind of represented as kind of a differential equation where you have these weird pulse factors. So these are, normally in differential equation, this kind of stuff would be pretty tricky to kind of do, but that's kind of what the mathematics was worked out. But basically, what they showed was a key convergence property, where they basically showed that under some assumptions on the natures of those f and g's, almost always the network converges. Okay, so all the x's kind of end up being synchronized. Then subsequent work, when sensor networks started and also some people kind of started revisiting this. What they did was they kind of so this original work had the assumption that everyone can listen to everyone. What these guys out of Johns Hopkins did was they basically said, what if I know the network topology? Okay, so this network has some graph G which I know, so not everyone can talk to everyone, but I know who can talk to who. And then kind of they essentially showed that convergence can happen under certain conditions on the graph topology. I'm not going to go to the math, but sort of that was another key result, which basically said if the network topology holds satisfies some properties, so the interconnect matrix of the network, its eigenvalues had certain properties, then things can work out also. So that was another result which came up. And so that was about convergence. So the way it kind of works out is I can have an ad hoc network whose topology satisfies certain properties. You let them start out. Initially, the phases are all over the map, but very soon they kind of just converge. Okay, and without any kind of central coordinator of any form. Or if you look in the time domain, what's happening is there's two nodes, and initially their pulsing is kind of apart. You can see the dotted line and the dashed line are farther apart, but by the end they kind of end up synchronizing. Another way of thinking about this thing is that if you can think of it as a phase space, where the time at which they are firing are coordinates in this phase space, and essentially what happens is, independent of where you start off with, they all get synchronized, so they actually all get attracted to a single point 0, 0 in the phase space eventually. Okay, so you may start out with a phase difference, but wherever you may start out, you end up at the same place. So what those guys, the original result was, in the phase space, where, irrespective of wherever you'll start, eventually you will move to this attractor point and you'll kind of stay there. So the protocol is actually pretty simple, and then some subsequent work in recent years have kind of made MAC protocols and all around kind of this basic idea. So bottom line, I guess as you can see, there are many different flavors of network synchronization protocols that have emerged over the years. They have different properties, they serve different application requirements. Sometimes they're just coming from different philosophical sources. And at some level, you could argue that, I mean, GPS is a network synchronization protocol. It's just structured differently. Not everything is under your control, but it's a great system. And if it were to only work indoors and be low power, then actually our time problems would be largely solved, but neither one of those two properties are true, so all this other work continues to be relevant. There is one of the US government agencies which kind of focuses particularly on location and these kind of things. Their stated mission is that by the year 2020 or so, they want US military to have the ability to have sub-millimeter level location knowledge anywhere on the planet. And to achieve that, the key thing, I mean, if you go back to that 1700 challenge by British monarchy on improving time to localize, to find the longitude, it's in the same vein. You will need very precise timing, and I think that's kind of just going to be the key. Okay, so so what's so that's one thing. The other thing which is happening is time is being used in many ways. So we kind of saw that sometimes we want global time sync. Sometimes we want to just know what was a good timestamp for something happened in the past. Systems sleep, then their time needs are different. So at different phases of a system life, you have different time needs and all. So time service, as we see commonly, I mean, our notion of a time service on something like Linux or Mac OS X is a very simple one. Tell me what time it is and sleep for some period of time. I mean, these are basically the two time primitives that we see as applications out here. But applications in the embedded space have a lot richer kind of things. Do the two actions together. Do this action followed by this action 1 second apart. I don't care when you do, but that sequencing should hold true. So there are many different requirements out there. So one of the things that's happening is there's a whole bunch of different abstractions for time services that people have explored, and we kind of saw that post facto synchronization was one, peer-to-peer, those kind of things are basically presenting time knowledge in different ways to the system. So new models for time basically that have been emerging. It's kind of, so what are ramifications? So let's say you have these things and all, what does it mean for our overall system? So at some level, applications are asking a relatively simple question: what is the time? Or some other similar question about time. And the system tries its best. It has a local clock, it has access to GPS, access to network services, and so on and so forth. But intrinsic in this is any answer related to time is going to be some sort of an uncertainty. And that uncertainty, usually we kind of let's say, for example, you tell your OS, sleep for 5 seconds or whatever, wake me up in 5 seconds. The OS doesn't know whether you really meant 5.00000 or would plus minus 10 millisecond be okay. That's one issue. And also, you don't know whether the OS will wake you up in 5 seconds precisely, or is it going to take some liberty and it might be 5 seconds plus minus 10 milliseconds and all, right? I mean, none of those things are visible to us, but nevertheless they are there. There is a delta out there, and in real-time systems and managed systems, we try to have more knowledge and more control over delta. That's what makes them different from our regular operating systems. So as these technologies like GPS, PTP, the precision time protocol, and all have coming in, a lot of people who work in distributed systems are kind of revisiting how system itself should consider time or look at time. So there's some recent quotes. Professor Ed Lee, who at Berkeley, who kind of does. There's a quote I picked up from one of his talk on YouTube. It says, "If you assume that clocks are synchronized and you have some sense of what the precision is, it changes everything." In the sense how you do distributed systems. Traditionally, all that logical clocks and all, this could be an alternative answer, and it can actually let you do things which you cannot otherwise. There are some faculty candidate talk, I think, this year in CS, which is kind of around this theme that if I have good precision timing, I get a very different visibility into what kind of bugs and things are happening on the internet, okay, because I can know things far apart, I can relate them together. This is another quote by a workshop which took place a couple of years ago. It says, "Several recent trends have exacerbated time-related problems by increasing reliance on technologies with intrinsic time variability." So what this is referring to is that a lot of new developments that are happening, they're great from some perspective, but they're also making our traditional time synchronization stuff work less effectively. Wireless communication is one. So wireless communication links have higher variability, higher asymmetries. So those are multi-core processors and other issues. Virtualization. So when you're running virtual machine, its notion of time versus the reality is actually a pretty complicated, weird thing if you look into how they actually maintain time relative to the host computer. So there are a lot of these technologies which are sort of complicating stuff, and at the same time they actually are also interesting. I capture some sensor data at my home, I ship it to Xively. If my home timestamp and Xively's timestamp are not synced, then of course that data is not very useful for someone else which is downloading. So now we are implicitly kind of relying on a shared synchronization across a whole bunch of users, right? I mean, when we are sharing sensor data, you're actually relying on everyone agreeing to a common knowledge of time. So they're kind of interesting. I mean, as we rely more and more on time type data, this is going to become more of an issue and more of a vector for attack. By manipulating time, you can kind of fool something also. From a system engineer's perspective, this notion of the quality of time, that delta that I kind of talked about, is I mean, one naive way of thinking about this is, hey, all I need is more accurate time. But as we saw, that's not necessarily the case, because different parts of the system may need time with different accuracies. So what happens is that many new applications are facing challenges that just making best time at all times is not the answer. You often need to kind of consider, kind of adapt to things. There's a mostly unreadable breakout of iPhone 3GS, but this showed that there are roughly 8 or 9 oscillators on it, some TCXOs, some not, some real-time type stuff, kind of a pretty complicated mix of timing even on kind of tinier devices. And then the other thing is that, as we saw, quality, the quality with which you know time affects your other system parameters, like, for example, the accuracy with which an acoustic sensor can localize a target or a sniper in a city setting, and also a lot of system operations do depend upon this. And there are many examples you can imagine of this thing where precise location depends on time, duty cycling, as we saw, depends on time. A lot of distributed systems, time is essential. Good knowledge of time is essential to their robustness. Imagine you are doing a control system, and control systems, as you know, do rely on sample time. That sample time in turn affects the parameters of the controller. If now imagine that sample time was actually not the correct one, in the sense that you think you were sampling at 1 second, but you're actually sampling at half a second, then the dynamics of the controller are going to be very different, and it may not converge. In some in a recent talk I heard some doctors were giving, one of the big challenges they face currently in a poorly designed hospitals currently is that they have all these medical instruments. They're all on the data from all of them are collected together, but their times are not properly synced. So oftentimes they kind of see some episode happening here at some timestamp, some other episode with the same patient on a different instrument, but the times are not reconciled. A lot of these are stupid problems, but what shows is that I think obvious is often overlooked in engineering also. Multimedia obviously depends very heavily on time. If you are doing different types of media coming together, they need to be synced. I'm sure you have seen those annoying instances where the sound and lips are slightly out of sync and kind of problems they end up causing. So in multimedia things, you want to keep that synchrony through the network. User experience, in fact, in a talk I was hearing, they pointed out that mobile gaming or network gaming is actually one of the more challenging things for time synchronization, because now you have multiple users all over kind of interacting with each other, and these are really real-time systems running over the network, and again, very tight time synchronized requirements. So time at some level is kind of creeping in. Some of you may have heard the talk, faculty candidate talk yesterday, which was on autonomous vehicles and all, and I was kind of talking to him. So they also have, like, everything in the car needs to be time synchronized, otherwise different processors are just not going to properly interact with each other. So one way of thinking about it from an operating system software perspective is that besides kind of our usual services that operating systems provide, they also provide a time stack of sorts. So just like we think of a network stack, I send a packet or web service and it kind of goes all the way down. Really hidden behind all this stuff in the OS is also kind of a time stack. And what's happening in this time stack, at the lowest level, you have an oscillator, you have clock generation, you have distribution of the clock. All of this is hardware. Then you measure time using counters and timers and stuff like that. You also have network synchronization stuff happening, which talks to other nodes or perhaps to things like GPS and all. Collectively, all this stuff is then fed into some sort of time-based services. So like the sleep for time, or what is the time, those kind of APIs that you have. So the services feed into APIs, and finally your application sits on top and kind of makes use of these things. So there's a very complicated stuff which is hidden from you. All you see as an application developer is something out here. When you're doing something like embeds and all, you begin to deal with the counter hardware and all directly, but usually that's where we stop. I don't think we ever go further down unless you are a hardware designer working on a COM chip and all. So a lot of our problems are often coming from the fact that the specs at these different layers, there's a high degree of variance. I mean, depending upon what the network characteristic is, the quality with which you will see time information will change. We saw that how time and how temperature and all those other things kind of affect what you see out here. And likewise, the OS characteristics, variability in the processing and all, they all kind of end up affecting things. So increasingly for very time critical applications, each one of these layers has to kind of adapt. So like the protocol adapts to ambient conditions. So we saw temperature, how you can kind of do some mapping to that. Network conditions, network topology, those kind of things. Lower layer, you can imagine the same thing as I alluded to, that there's compensation. You can switch the resonator you're using, all those kind of things that are happening. Fundamentally, from the system level, you are sitting up here, you have some requirement, so you might say, wake me up at 5 p.m. and by the way, I can tolerate an error of 10 milliseconds. And then somehow you expect all of these things to kind of obey that. And the reality at this stage is that when you say, wake me up at 5 p.m. on a machine like this, it's entirely a best effort notion. Okay, I mean, what's happening is this machine may or may not be using NTP at the time. You don't know what kind of clock it is. So when it wakes you up at 5 p.m., you really don't know what quality, what's uncertainty associated with it. But you do at some level have a contract. I mean, when you're saying wake me up at 5 p.m., you are making a contract, and I guess currently the assumption would be when I say wake me up at 5 p.m., I'm saying wake me up at 5 p.m. precisely, but obviously that's not the case. So in real-time systems, that begins to happen is that you have to specify something more precise. You have to begin to kind of go into that uncertainty somehow, and then you expect the system to kind of do something about it. Again, not much happens, but that's what kind of the expectation would be, that as I, like for example, as I need more accurate time, perhaps the system can start activate the GPS, do more frequent network synchronization, perhaps wake up a higher quality clock. All those kind of things would ideally happen. So you could imagine kind of the system auto-tuning all of these things away. They don't, other than in very limited ways, but that's what you would ideally like to have. Time is also a vulnerability. So if you can attack time, then you can attack a lot of other things, right? I mean, so if your computer suddenly thought it was at in a different time zone, or was just different, things break down. In fact, by manipulating these things, people have shown attacks with which a lot of common applications have a hard time dealing with. So you could imagine non-invasive attacks on clock sources. So we have seen that temperature affects clock. Okay, so you could imagine that if there are nodes which are unattended, maybe you can put a heater near them, and now their clock will, if they're using a cheap oscillator, which most of them do, then if they're not network time synced, which most of them are not, the sensors and all, you can actually cause change in sample rate and other kind of stuff. You could do worse. So our time protocols relied on delay measurement, right? So a node would send a packet, timestamp it. Another node out here would receive and timestamp it. Now imagine in between there is some bad guy, and what it does is it jams the sender's packet, but grabs the packet, and then after a few seconds of delay, transmits it, and this guy gets the packet, right? So all that has happened is we have inserted additional physical delay. And that would mean that the two parties will think that their time offset is different than what it really is. And now, if they were, let's say, two nodes which were supposed to fire a weapon and bring down the missile jointly, now they were actually firing at a different time. So, and in this case, cryptography doesn't help you because you're never modifying the packet. You're only delaying the packet. So if you can make that happen, you can do kind of interesting kind of attacks also. So these are called meaconing attacks. Okay, so basically all you're doing is you're inserting an additional delay in the transmit path and kind of manipulating stuff accordingly. Whereas here you're changing the clock source. There are other kind of attacks that one could imagine, and the systems currently are actually not really protected against those. At the same time, there are perhaps some interesting things that the system can do, and people are kind of doing that as well. So look at operating systems. All operating systems, or many common operating systems, general purpose OSs, rely on this notion of a tick, which is usually 10 milliseconds, 20 milliseconds, something like that. And every so often, and the system, the OS kind of at that tick does a lot of housekeeping work. So at this tick, the OS might excuse me, the OS might reschedule tasks. It might also take care of events that are pending and all. So, for example, when I gave the example on Linux, when I said wake me up after 5 seconds or wake me up at 5 p.m., it actually is never going to be precise because we know Linux has, I don't know what precisely they use, but I think somewhere around 10 milliseconds or so. So right there is an inevitable granularity because the OS doesn't even check for the timers and rescheduling unless it's that boundary. Some of the work in recent times, some of you may have heard of something called tickless kernel or tickless in Linux, and that basically referred to the fact that when the system is not doing anything and all, I'm still kind of doing this tick, and that kind of starts causing problems. So things that are happening are perhaps my tick rate should be dynamic, perhaps the uncertainty I should take into account the uncertainty when I'm kind of creating this tick, so that when an application says 5 second, you ask it, is it 5 second plus minus 100 millisecond, or is it 5 second plus minus 10 millisecond? And that knowledge could be used out here, because if it is 5 second plus minus 100 millisecond, your tick could actually be a lot slower than what it normally is. So some folks at CMU have been exploring quite a bit in this work, and they've kind of shown that there are energy gains to be had, because by slowing down the tick rate at the OS level, then while the OS is idling, you actually lower the energy consumption. So new abstractions with which tasks can be specified. So you can imagine in real-time systems, in a rate monotonic framework, for example, when you specify a period or a deadline, you may actually specify some uncertainty with it, and the OS can exploit it by changing this underlying tick, for example, or just generally kind of controlling the hardware accordingly. Mac OS X, the latest Mac OS X, the Mavericks, which came out, as some interesting things. So one thing that happens in systems is that oftentimes there are a bunch of tasks, and they all mention things like wake me up at this time, wake me up at this time. So if you look at the request for time events, they kind of look like some random junk. But since the tolerances are much more relaxed, at least for kind of things that run, what you can do is you can excuse me, you can align them in time. So you can align them in time so that your CPU, instead of kind of being up most of the time, can now have more sleep opportunities. So by taking these requests from applications for their deadlines and all, and then subjecting them to some sort of a tolerance specification, you can then coalesce things so that they are better aligned in time, and so that you have a better opportunity to sleep. So this was one of the things Apple touted as a mechanism that they have for better power management in their newest OS. Windows 8 also has something similar. They just call it something differently. So timing aware task scheduling more generally can kind of result in things. You can kind of essentially shift things around in a real-time system. Maybe I can delay a task until a little bit later so that I maximize the sleep time opportunity. So generally speaking, a lot of interest currently that there's an interplay. If I know more about what application really wants, and if I know more about what the hardware can actually provide, I can maintain the illusion of good quality time, but at the same time kind of improving system performance quite a bit. And so that brings me to the end of time synchronization. So what has happened thus far is many protocols with many prototype implementations really kind of, I would say almost like phase one was NTP in the network setting. Phase two was these newer precision stuff, PTP, and the stuff which came out of wireless sensor networks and all. At this stage, as we saw, we can synchronize nodes to within microseconds if you are in a local area. If you are at a planetary scale, then you are at, if you can use GPS, then you are again in some microsecond. If you cannot use GPS, if you have only internet, you are probably tens of milliseconds. We can provide network-wide time sync, but it's not always necessary. It can be very wasteful. By optimizing the clocking system, you can actually match it to your application needs quite a bit. Some of the issues, secure time sync. So time synchronization, generally speaking, is a fragile component of our system, and we kind of rely on it. As one worries about time, you have to kind of optimize it for your particular application needs. Or another way of saying it is, if you're designing a system, then instead of providing just a global time sync service, you probably need to provide a richer set of services that the applications can use. New types of clocks, I referred earlier, MEMS clock and all are emerging. Chip scale atomic clocks have also kind of made a huge difference. They're not widely available because of it's a technology not for export and all, but it certainly is making a big change. And more generally, kind of as time becomes more and more important, and people, so at one level, time is becoming more important for many applications. The flip side is that people are realizing, as that quote by Edward Lee, which is that if I have knowledge of time, I can do things differently. Okay, traditional things differently, and I think that's kind of a powerful thing also. So it's kind of resulting in kind of people making better use of knowledge of time for network debugging, for understanding network performance, for optimizing power consumption in the OS. There are a lot of other places one can kind of make use of that. So that's the story on time. And I'm going to stop out here, and we finished early, so I'm not going to start a new topic today. We'll pick it up next week. We'll talk about security in a minute.